Good day, everyone. Today we're going to continue our discussion on factorial designs, specifically two-level factorial designs. And today our topic is two-level fractional factorial design. Previously, we talked about blocking a replicated 2 to the k factorial design, as well as confounding in the 2 to the k factorial design and partial confounding. And remember that the motivation behind these different methods are basically one, that you don't have enough resources to run the complete replicate, say in one block for confounding, or you just cannot run all the experimental runs with one batch. Okay, so with that motivation, okay, you have to implement blocking. Okay, and sometimes you also want to deliberately change the conditions in the experimental design so that you can sort of replicate, okay, what is observed in practice. For partial confounding, this is useful when you have a moderately large value for k, and you need to replicate. Okay, so for you to be able to obtain some information on most variables, okay, most factors, then what you basically do is to have a different effect to confound the blocks with. Okay, and with that you can have a relative information, okay, relative partial information on several effects, okay, that you choose to confound with. Okay, so for Unit 4, these are the topics. Okay, first is the 1/2 fraction of 2 to the k designs, and then we'll build on that and talk about 1/4 fraction and generalize our discussion to the general 2 to the k minus p fractional factorial design. After that, we're going to talk more about alias structures and different design resolutions, specifically 3, 4, and 5, and then the supersaturated designs, and finally we'll talk about the Yates method. So first, let's talk about when do we need fractional factorial designs. Okay, so you know that when you have several factors to consider in your experiment, okay, when k is high, okay, then, or as k increases, okay, then the number of runs per complete replicate also increases. An increase in number of runs per complete replicate would of course mean increase in the amount of resources that you will need for your experiment. Okay, so let's illustrate that in, say, a 2 to the 6 factorial design. That is, you have k is equal to 6. One complete replicate would entail 64 runs. All right, 64 runs for just one replicate. And you have to take note that of the 63 degrees of freedom, okay, from these 64 runs, only 21 are potentially important. And this 21 is constituted by 6 main effects, okay, and 15 two-factor interactions. So these are more likely the major effects of interest in your experiment. But you do have 63 degrees of freedom. So in most cases, as I mentioned in the previous unit, higher order interactions are less likely to be of significance. They're usually negligible. So if it can be assumed that certain high order interactions are negligible, it is possible to obtain information about the main effects and low order interactions by running a fraction of the full factorial experiment. And by doing so, you reduce the amount of resources that you will need for your experiment. Now, of course, it is particularly useful when it is difficult or impossible to run all treatment combinations. So where are fractional factorial designs being used? The major use actually is in screening experiments where you're interested in a lot of variables, but you first want to determine which variables, which factors would actually have significant or interesting effect on the response variable. Fractional factorial designs are used in product and process design, process improvement, as well as industrial or business experimentation. Now, there are three key ideas behind fractional factorial experiments. The first one is the sparsity effects principle. Okay. The second one is the projection property. And then the third is the sequential experimentation. So first, I will define each of these key ideas. Okay. And then as we move along with the lecture, we will illustrate this. So let's first look at the sparsity effects principle. In designs with moderately large number of factors, it is highly likely that the main effects and low-order interactions will be of significance, as we mentioned earlier. So that is basically the sparsity effects principle. Now, this statement was taken from Montgomery, Design and Analysis of Experiments, about the projection property. So it states, fractional factorial designs can be projected into stronger, that is larger, designs in the subset of significant factors. So with the use of the fractional factorial design, you can potentially identify a subset of significant factors and later on project it into a larger design. And then you have sequential experimentation. Again, this statement is from Montgomery, Design and Analysis of Experiment. It is possible to combine the runs of two or more fractional factorials to construct sequentially a larger design to estimate the factor effects and interactions of interest. Okay, so if, say for example, later on you realize that you have enough resources to run, okay, another fraction of the factorial design, then you can come up with a larger design, okay, and therefore be able to estimate further factor effects and interactions of interest. Okay, so now let's start with 1/2 fraction of the 2 to the k design. We will kick off our discussion on 1/2 fraction of the 2 to the k design with a discussion of the basic definitions and principles. Okay, so let's start with this example. Now, suppose that you would like to investigate 3 factors, each at 2 levels. However, you do not have the resources to run all 2 to the 3 combinations, so 8 combinations. You can say, for example, run only 4 of the combinations. So that means that you can only run 1/2 of the full factorial design. That is, in the terminology of factorial design, you can run a 2 to the 3 minus 1 design. Okay, and of course this has 3 degrees of freedom, okay, related to the 4 combinations. Okay, now if you look at the table of plus and minuses, okay, of the 2 to the 3 factorial design, okay, you will notice that the column of ABC, okay, the upper half of which with all pluses, okay, would also correspond to your identity column, okay, which also has all pluses. And to obtain the 1/2 fraction, okay, we choose that those combinations with plus signs under the ABC column. All right, so in this example, ABC is our generator, and the generator is also known as the word. Okay, so just to be familiar with the definitions and terminologies. Okay, so in this example, since ABC is our generator, it's also known as the word. Okay, and we choose these combinations with plus signs under ABC. Okay, and we also have to define, okay, or we also have to be familiar with the term defining relation. This is basically the set of all columns that are equal to the identity column. So in our previous example, as you saw, okay, ABC has pluses, all plus here, okay, for the 1/2 fraction of the factorial design. And this is equal to the identity column, which always has plus signs, okay? Therefore, in this example, our defining relation is I equals ABC, okay? Now let's move on to effect estimates. All right, so to estimate the main effects A, B, and C, okay, we use the table of plus and minuses. And for main effect A, okay, then we have 1/2 of this expression here, and we know that this would just come from the table of the signs of our treatments here. The total of observations for each treatment combination would just come from the table of plus and minuses. So for example, for main effect A, you have A, okay, that it has a plus sign, minus B, okay, minus C, plus ABC, okay. And then we just do the same thing for B and C. Okay, take note of the notation here. The main effects now are enclosed in brackets, and we will explain that later on. Okay. Now let's look also at the two-level interactions. Okay. So again, we just look at the 1/2 fraction. For the two-level interactions, you can see that for BC, you have A minus B minus C plus ABC, okay? And so on for AB and AC, all right? Now, if we compare this to the expression for the main effects, you will notice that the expression for A is identical to that of BC, expression for B is identical to AC, and expression for C is identical to AB. Okay. Effects, okay, effects with identical effect estimation expression are actually called aliases. So in our example, A is an alias of, or BC is an alias of A, AC is an alias of B, and AB is an alias of C. Actually, when you are estimating A, you are actually estimating A plus BC in this case. And then when you're estimating B, you're actually estimating B plus AC. When you're estimating C, it's actually C plus AB. Okay, so that is a characteristic of aliases. Okay, so in terms of notation, so when you have this bracket here, okay, the main effect, it actually pertains to A plus BC. So for example, B, okay, with alias AC, this estimate actually captures B plus AC. C in brackets is C plus AB. Okay. Now, how do you obtain aliases? Okay, the alias for any column is the product of the defining relation, okay, for our example, I equals ABC, and the column of interest. So for example, the alias of A, okay, to obtain the alias of A, we multiply it by the identity column. Okay, so this would now be, and we know that the defining relation is I equals ABC. Therefore, this is just equal to A times ABC. Okay, and square of any column is also equal to the identity column. Therefore, this would be equal to I squared BC, and therefore this is also equal to BC. Okay, and we know that BC is the alias of A. Now let's move on to differentiating principal fraction versus complementary fraction. Okay, the fraction corresponding to pluses is the principal fraction. Okay, now of course the alternate fraction, or the other half, okay, the other half is called the alternate fraction or the complementary fraction, and it has the defining relation I equals negative ABC. Okay, so in terms of notations, the effect of main effect, the estimate of main effect A coming from the complementary fraction is denoted as A brackets enclosed in brackets apostrophe, okay, and this is basically equal to A minus BC, okay, and so on. Okay, so note that you can use either fraction because they belong to what is termed as the same family. Okay, so they belong to the same factorial experiment. So you can either choose the principal fraction or the complementary fraction. Now let's move on to the aliasing after running all fractions. So for example, say for example that you were able to perform a sequential experiment where first you took the principal fraction and then you were able to perform also the complementary fraction. And as a consequence, you actually already have a full factorial experiment. Now, the question is, how do you obtain the actual estimate of the main effects? So you can do that by de-aliasing, okay, de-aliasing the effects. So for example, you have from the fractions, you have these expressions for the main effect A. Okay, so from the principal fraction, you have this expression, and then for the complementary fraction, you have this expression here. Okay, from these expressions, you can actually obtain the main effect for A for the full factorial by getting 1/2 the sum of the main effect from the principal fraction and that from the complementary fraction. So this would just be equal to 1/2 the quantity of A plus BC plus A minus BC. Okay, and that would just be equal to A. Of course, you can also obtain the effect for the two-factor interaction BC, which is the alias of A, by using 1/2 times the quantity main effect from the principal fraction of A minus the main effect from the complementary fraction also of A. And this would just be equal to 1/2 the quantity of ABC minus A minus this expression here, A minus BC, and this would just be minus A plus BC, and simplifying this, you would just get BC. In general, after running two 1/2 fractions of a 2 to the 3 design, you may obtain the effect estimates as follows. So let I be the effects A, B, and C from 1/2, okay, I plus I complementary, you would get the main effects, and then from 1/2 I minus I complementary, you would get BC, AC, and AB. And note that in the principal fraction, you have the defining relation I equals ABC, while in the complementary fraction, you have the defining relation I equals minus ABC. And therefore, AB is actually confounded with blocks in the full factorial. Okay, so now let's move on to the definition of a design resolution. Okay, resolution R in general means that there are no p-factor effects, okay, that are aliased with another effect containing less than R minus p factors. So for example, in a resolution in a resolution 3 for 2 to the 3 minus 1 design, okay, there would be no main effect, that is no one factor effect, okay, that is aliased with other R minus P, that would be 3 minus 1, okay, so less than 2 factors. So that would mean no main effect is aliased with other main effects. Okay, so for example, another example in resolution 4 for 2 to the 4 minus 1 design, no main effect, okay, when P is equal to 1, can be aliased with 2 factors and other main effects, because that would be 4 minus 1, okay, so that is 3, okay, so less than 3, that would be 2 and 1. Therefore, no main effect can be aliased with 2 factors and other main effects. So, basically, the design resolution is the shortest word in the defining relation. So, recall, for example, in our 2 to the 3 minus 1 design, okay, it is a resolution 3 design because you have the defining relation I equals ABC. The word is ABC and its number of letters is 3. Okay, so you can actually also call a resolution 3 design as a 3-letter word design, resolution 4 as a 4-letter word design, and 5 as a 5-letter word design. Okay, so let's go through the definitions of resolution 3, 4, and 5 designs given our recent discussion. Okay, so for resolution 3, the main effects cannot be aliased with each other. The main effects can be aliased though with 2-factor interactions, and the 2-factor interactions can be aliased with other 2-factor interactions. So an example of this would be the 2 to the 3 minus 1 design with the defining relation I equals ABC. And the notation would be like this. You have 2, and then the superscript would be 3 minus 1, indicating that it's a 1/2 fractional factorial. Okay, and 3 here, the Roman numeral, indicates the resolution of the design. And then resolution 4, in resolution 4 designs, the main effects cannot be aliased with each other or with 2-factor interactions. But 2-factor interactions can be aliased with each other. Okay, so an example would be a 2 to the 4 minus 1 design with I equals ABCD. Okay, and lastly, for resolution 5, the main effects and 2-factor interactions cannot be aliased with each other. The 2-factor interactions can be aliased with 3-factor interactions. And an example is a 2 to the 5 minus 1 design with I equals ABCDE. Now, of course, it is recommended that the highest design resolution consistent with the degree of fractionation possible is adopted. And the implication of this is that you would be less restricted in terms of the assumptions on which effects are negligible when making unique interpretation of the results. Now let's proceed to the construction and analysis of the 1/2 fraction. Okay, so let's first talk about the construction of the 1/2 fraction for a 2 to the k design. Okay, so there are 2 main steps. The first step is for you to formulate the basic design. And the basic design basically contains the runs for all, for a full 2 to the k minus 1 design. Okay, and then the second step is to add the kth factor by using the plus and minus signs of the highest order interaction. That would be AB to k minus 1. And then the alternate design is obtained basically by using the opposite sign. So it's just minus the generating factor for the principal fraction. Note that you can actually use any of the effects to generate the fraction. However, using AB to k minus 1 to generate the kth column results in the highest possible resolution. Okay, so let's take the case of 2 to the 3 minus 1 design. That is a fractional factorial, 1/2 fraction of the 2 to the 3 factorial design. So as we mentioned earlier, first we construct the basic design. So in this case, this is the basic design where we have the runs for a full 2 to the k minus 1 design. So 2 to the 2 design in this case, right? So we would have factors A and B, and we would have then 4 runs for this 2 to the 2 full factorial design. Okay, so that would be the basic design. And now to generate the principal fraction for the 2 to the 3 minus 1 resolution 3 design with the defining relation being I equals ABC. Okay, we just add the column for the third factor, which is C, and this would be equal to AB. Okay, the signs under this column would just be equal to the product of the signs for AB. Okay. In other words, okay, the kth factor is generated by using the plus and minus signs of the highest order interaction for the 2 to the k minus 1 full factorial design, and that would be in this case, okay, is AB. All right, so C is equal to AB, and we just get these signs by multiplying the signs under the columns A and B. Now for the alternate fraction, we basically just get the negative ABC. Okay, so you have plus, minus, minus, plus here, therefore you have minus, plus, plus, and minus over here. Now, another way to look at 1/2 fractional factorial designs is that the runs are partitioned into 2 blocks with the highest order ABK confounded. Okay, so each block consists of the 2 to the k minus 1 fractional factorial design of the highest resolution. For our 2 to the 3 minus 1 example, the 2 blocks are confounded with ABC. Now let's talk about projection of fractions. Okay, now any fractional factorial design of resolution R contains complete factorial designs, possibly replicated factorials, in any subset of R minus 1 factors. This statement is from Montgomery. Now suppose you believe that only R minus 1 factors from a set of several factors are important. Then, a fractional factorial design of R resolution is suitable. Now, if the design is correct, it can be projected into a full factorial in the R minus 1 significant factors. This is illustrated in resolution 3, 2 to the 3 minus 1 design, which projects into full 2 to the 2 factorial design for every set of 2 factors. Now, since R is equal to K is the maximum possible resolution of a 1/2 fractional factorial of a 2 to the K design, every 2 to the K minus 1 design will project into a full factorial in a K minus 1 of the K original factorials. Okay, so we will illustrate this later on with an example. Okay. Moreover, 2 to the k minus 1 design can be projected into a full factorial with 2 replicates for any subset of k minus 2 factors, or 4 replicates for any subset of k minus 3 factors, and so on. Okay, so let's look at a particular example to illustrate what we have discussed so far. And let's go back to this original example on filtration rate of a chemical product. Okay, so I will not read the text anymore because we recently also talked about this in Unit 2-3. So these are the original observations for the different treatment combinations. For this 2 to the 4 full factorial single replicate the experiment. Okay. And now, suppose that you can only run 1/2 of this experiment. Therefore, you can only have a fractional factorial you can only run, okay, 1/2 fractional factorial design. Okay, so in this case, you have a resolution 4. This should be 2 to the 4 minus 1. So you have a resolution 4 to the 4 2 to the 4 minus 1 design, okay, for this filtration rate of a chemical product example. And the defining relation, in order for us to be able to achieve the highest resolution for this particular experiment, which is resolution 4, the defining relation is I equals ABCD. Okay. Now, to construct the 1/2 fraction, remember that the first step is to formulate the basic design. This would contain the runs for full to the k minus 1 design. In this case, 2 to the 4 minus 1. Therefore, our basic design would correspond to a 2 to the 3 design. Okay, so this is how it would look like. So we have 3 factors A, B, C, which would have a full factorial of this design would have 8 runs. Okay. And then the next thing to do is add the kth factor by using the plus and minus signs of the highest order interaction a, b to k minus 1. So that would be ABC. And then the alternate design would just have negative ABC. Okay, so for the principal fraction, we add the kth factor, which is D, and this would just be the signs would just be the signs for A, B, C. Okay, so we just multiply the signs under A, B, and C here to get all these signs under column D. And so looking at this, okay, we can now identify the treatment combinations, okay, corresponding to the runs. So here, since all of the factors are at low level, we have treatment combination 1, and then you have high level of A, high level of D, and then low level of B and C. Therefore, you have AD, and so on. Okay. We can also already identify the aliases. Okay, so in this case, we have 4 main factors aliased with 3-factor interactions, and 3 2-factor interactions aliased with 2-factor interactions. So let's go through these aliases. So for A, the alias is BCD, and as we know, this is just obtained by multiplying A with the defining relation. Why? Because the defining relation is basically I is equal to ABCD. So it's like you're multiplying A with identity. Okay. So A times I is basically equal to A times ABCD, and this is also equal to I squared BCD, which is also equal to BCD. And you just do the same thing for B times the defining relation, C times the defining relation, D times the defining relation, and you get the aliases for B, C, D as ACD, ABD, and ABC respectively. And then doing the same thing for the 2-factor interactions. For example, AB, you multiply it by the defining relation, you get I squared CD, which is just equal to CD. Therefore, AB is aliased with CD, AC with BD, and BC with AD. Okay, now this 7 aliases correspond to actually the 7 degrees of freedom for this design. Okay, now so we now have the 1/2 fraction. Okay, we now know what treatment combinations we are to run. Okay, these values are obtained from the original given data, but of course always randomize. In reality, always randomize the runs. Okay. Okay, now let's proceed to the analysis of the 1/2 fraction factorial for this experiment. Okay, so let's illustrate the estimation of the main effect A. So for the main effect A, okay, the expression would just be equal to 1/4 times the contrast, which is, for this case, -1 plus AD minus BD, and so on. Okay, so that's why you have this expression here, and you just obtain, you just substitute the values for these combinations, okay, over here, and you get 19 for main effect A. And remember that this is actually A plus BCD. Another example, so say you want to get the interaction AB, okay, so AB would have the sign which is equal to the product of the signs under column A and column B. So that would be minus times minus, plus, plus times minus, minus, and so on. Okay? And then we just again substitute the values, and eventually we would get AB equal to -1. And again, this one is equal to AB plus CD because AB and CD are aliases. Okay, and if you perform the similar calculations for all the main effects and the interactions, you would get these values. Okay, and you will see that the significant effects, okay, as shown in boldface here, are A, C, D, AC, and AD. So these are the ones that have large estimated effects, okay, in this experiment. Okay. Now, how do we interpret this given that this is the alias structure? Okay. So, okay, let's see. So A, C, D, AC, and AD. Now, it is safe to assume that the higher order interactions are negligible. Therefore, A, C, and D, the main effects A, C, and D are likely the significant effects as well. Now, consequently, because these main effects are significant, then with these values as well, then it could be safe to conclude that AC and AD are also likely major effects, okay? And that BD and BC are likely negligible because you see here AC and AD, okay? And AC is AC plus BD, okay? Bracket AD is AD plus BC, okay? Since AC and D, the main effects AC and D are large effects, okay? Then interaction of AC and AD are also likely large, the effects of which are also large. With that, we can safely conclude that BD and BC are likely negligible in this case, okay? And then with AB having a very low estimate here, the simplest interpretation would be that AB and CD, okay, also have low effects, okay? And we recall we use Occam's razor as principle, okay? So this is a scientific principle which basically states that the simplest interpretation is usually the correct one. Now, we also conclude that AB is probably negligible by weak heredity, no? Because only A with the interaction AB is significant. Okay. Now, therefore, we can project the resolution for 2 to the 4 minus 1 design to a single replicate 2 to the 3 full factorial using the significant factors which are A, C, and D as shown in this geometric representation. Okay, and with that also we can generate a regression equation, okay, that could help us predict, okay, the response variable, and the response variable which is filtration rate, and that expression or that regression equation would be this, okay, where you have y hat is equal to b naught hat plus b1 hat x1 plus b3 hat x3 plus b4 hat x4 plus b13 hat x1 times x3 plus b14 hat x1 x4. And x1 corresponds to factor A, x3 corresponds to factor C, and x4 corresponds to factor D, which are temperature, concentration, and steering rate respectively. And these two expressions or terms correspond to the interaction between temperature and concentration, and then temperature and steering rate. Okay, recall that B naught hat here is basically just the average of all observations. Okay, so 70.75 is the average of all the observations here. Now, to get the other parameters, we recall that x1 here are coded variables, okay, and they take on the value from -1 to 1, okay. For the parameters beta 1, beta 3, beta 4, and so on, okay, we just get 1/2 of the effect estimates, okay. So for B1, the effect estimate corresponding to A is 19. That's why we have 19 over 2 here. And then for B3, the effect estimate for C is 14. Therefore, we have 14 over 2 here, and so on. Okay, so that's it for now. We're going to continue the discussion in a succeeding video.